Okay, so hello everyone. Welcome to the 7th day of our Alumni Lecture Series. Today, we are delighted to have Aritra as our speaker. He did his bachelor's from Presidency University, and later he joined the University of Groningen for his MSc. And after that, he went to Yale University and he is a PhD student there. So today he will be talking about Un-BlackBox-ing, machine learning algorithms, and astronomical perspective. So let's hear from Aritra.
Okay, hopefully you can see my screen.
Yes, we can.
So good evening to everyone back in Kolkata, and good morning if you're joining this from somewhere else. Thank you. At first, thank you, Nomonita, for the introduction. And I'm very happy to have the opportunity to be speaking in this colloquium series today. All the talks in this series have been very good. I've seen some of them on YouTube. I've attended some of them. And I will try to live up to the high bar that has been set by all the previous speakers in this series. So as Navanita mentioned, it's also special to be speaking today because I did my bachelor's at Presidency from 2012 to 2015. And I was yesterday trying to find a single picture which had almost everyone in our batch together in one frame. And I could not find one picture, but I think I managed to find everyone in our batch that I did my bachelor's with in these two frames. And it's great to be able to come back to a place and give a talk where I learned most of the physics that I know today. And I am also very happy to see some of the people, at least Pritha, Shumon, Chottanu, that's what I saw in the participants list, and maybe some other people joining the talk today. So with that said, let me jump into the topic for today, which happens to be un-BlackBox-ing machine learning algorithms. Now, the reason that I chose this topic for today is perfectly summarized by this meme in the next slide. So let me do something which should never be done, that is explaining a meme, but let me explain the meme in general. So machine learning is kind of a combination of computer science and statistics, and mathematicians and some other people who do theoretical statistics or theoretical computer science often scorn at the fact that all aspects of machine learning are not interpretable or understandable. So what I want to do in today's talk is kind of push back on that narrative a little bit, that machine learning algorithms are either difficult to understand or they are these black boxes which cannot be interpreted. So today, what we will be doing is essentially taking a peek into this black box, the inner workings of this black box. And as an example, what I will be using is a convolutional neural network that we have developed at Yale over the last 2 years, into which if you feed images of galaxies, as an output, you get the galaxy morphology, which is just a fancy word to say what is the shape of that specific galaxy. I am a third-year graduate student going to my fourth year at the Department of Astronomy at Yale University. I work in Professor Meg Urey's group, and Amrit, Chuan, Kevin, Dennis, and Meredith are some of the other people that have collaborated with me on this project. So before I go into machine learning or convolutional neural networks or any of that, what I want to start with is by telling you why are we interested in galaxy morphology. But before we can do that, I have to tell you a little bit about two additional things, which are galaxy color and galaxy mass. Now, Normotadi and Kostov in their previous talks spoke at length about galaxy colors, galaxy masses, so I will not go into too much detail. But what I will try to do is just to explain in one slide what do we mean when we refer to the color and mass of a galaxy, and it will become clear in a second why I am talking about the color and mass of a galaxy. So what do we mean when we refer to the color of a galaxy? What this image is showing one of the various pathways that a single galaxy can go from forming stars to not forming stars. And what you have on the x-axis over here is different redshifts, or so as to say, just different instances of time. So redshift 0 is the most recent, so that these are the oldest galaxies from the starting from the formation of the universe. And as you go higher and higher redshift, you are kind of stepping back in time. What I want you to do for this image is not pay any attention at all to what's happening in the middle, because that's just a pathway, and that's one of the available pathways by which galaxies can go from becoming star forming to becoming quenched. But what I want you to do is kind of focus on at the edges of the pictures. So on the very left, you have a galaxy which is completely blue and is forming stars at all radii. And on the extreme right, you have a galaxy which is red and is not forming stars almost at all, and it is what we refer to as a quenched galaxy. So the takeaway from this slide is blue galaxies are star-forming galaxies, and red galaxies are usually quenched galaxies that have no or little star formation. And we are not talking about dust or any other thing, so this is just understanding that from a very basic level, that color can give us a very primary indication of the level of star formation in a galaxy. So that's all that we need to know about color. The next thing that comes up is the stellar mass of a galaxy. So what do we mean when we refer to the stellar mass of a galaxy? So in the universe, there are these things called dark matter halos, which you can think about as just gravitational potentials floating around. And gas clouds within these dark matter halos collapse to form stars. With time, more and more gas collapses, and the galaxies start growing in mass and also sometimes size. This is not the only way galaxies can grow in mass. Galaxies sometimes also merge together to form a different galaxy, and that is also another way that galaxies can grow in mass. So essentially, there are two things that you want to take away from this. The color of a galaxy tells you the rate at which stars are being formed within that specific galaxy. And the mass of a galaxy tells you or gives you an indication of the stage of the hierarchical growth that the galaxy is in. So that's the takeaway from these two slides. The next that I'll be talking about are galaxy shapes or galaxy morphologies. Why are we interested in them? And to do that, I will show you a simulation. In the simulation, you will see two disk galaxies merging with one another, and you will see what happens when at the end of that process. So this is from the gadget simulations. And you can see now a single disk galaxy on the frame, and now you see a second disk galaxy, and they will start interacting with one another right here. So they have already interacted once. Now they're going to come back again and do a few more interactions. And now what you see is that you started with two disk-dominated galaxies, and the resultant galaxy that you end up with has nothing that resembles a disk anymore. So essentially, the thing to take away from this slide is the fact that, and let me also mention that whatever happened there, that two disk galaxies merging to form a bulge-dominated galaxy or an elliptical galaxy, is not by chance. This is something that happens all the time. That is to say, disk-dominated galaxies do not survive major mergers. So in essence, if anywhere in the universe you see a disk-dominated galaxy, you can be pretty sure that the galaxy did not have a major merger in the recent past, because if it had had a major merger, the disk would not have survived. So now what you have done is you have taken galaxy morphology or galaxy shape, and now you are using it as a proxy for galaxy merger history. So that is why inherently morphology contains much more information than just the shape of the galaxy, and is also helpful in this way for us to interpret galaxy evolution. Now, how exactly does it help us to interpret galaxy evolution? To make you understand that, I have to bring in galaxy color and galaxy mass, which I had spoken to you about just a few minutes ago. So let's go back to the slides and take a look at the color mass diagrams of a galaxy. This is from Shawinski et al. 2014. I will be showing the morphologies and everything. So this is from the Sloan Digital Sky Survey. And this is at redshift 0. And the morphologies were determined with the Galaxy Zoo project for this work. Now, let me first take some time to explain what's going on in this diagram over here. So on the y-axis, you have colors plotted. The lower colors are blue and the upper colors are red. And on the x-axis, you have stellar mass. Now, let me explain exactly what is going on over here. What are these things? So essentially, this is nothing but you can think about this thing as a scatter plot. But since there are so many galaxies here, instead of plotting points, what we have plotted, what the authors did is they plotted contours so that the density of the colors that you see, or the brightness of the colors that you see, correspond to the density of points. So the red color signifies the largest amount of points, and then blue, and then green, yellowish green, and then finally white. So these regions almost have no galaxies, and these regions contain a dense clump of galaxies. So once you have understood this picture, so essentially this is a color mass diagram of all galaxies at redshift 0 in the Sloan Digital Sky Survey. So what you see in this picture is this bimodal distribution. You have this, what we call a blue cloud, and this is just by coincidence, the color is blue. The color refers to the density of the galaxy. So you have this clump over here, which is we call a blue cloud of star-forming galaxies because they're blue. And over here, you have another clump, which we call the red sequence of quenched galaxies because they're red and not forming stars. In between these two distribution peaks, you have kind of this valley kind of region, which we refer to as the green valley because of the lack of galaxies in this region, and also because they're between blue and red. Now, what can you interpret about galaxy evolution from this picture? Remember that I told you this is at a fixed redshift. This is at redshift 0. So essentially, this is a snapshot of the universe at a particular instant in time. So what you can infer from this picture is that galaxies in the blue cloud may be quenched rapidly through the green valley into the red sequence. That was the standard paradigm of understanding of galaxy evolution till 5-6 years back. Why am I saying that galaxies quench rapidly? How do I infer that from here? Because again, if this is a snapshot at a single instance of time, and if indeed this was a slow process, then just by chance, since this is just a snapshot, a random snapshot, you would have seen also galaxies over here if this was indeed a slow process as well. Now, this standard paradigm of understanding completely breaks down when you bring in galaxy morphology into the picture. So what I'm going to do now is make the same plot, but now divide it into two panels where each panel will have a bulge-dominated galaxies and disk-dominated galaxies separately. So what you see over here is on the top, in the bottom panel, I have only plotted galaxies over here, which are disk-dominated, and I've taken the galaxies that are bulge-dominated and plotted over here. And as you can see, you completely no longer have the bimodality or the bimodal distribution anymore. What you see for the disks is, since there is no bimodality, what we can infer from this picture is that the disk-dominated galaxies grow in mass, and this is a secular process because there is a continuous density, and it keeps growing in mass until it reaches a certain threshold mass, after which the galaxy quenches a little bit faster and goes on to become red. But by all means, this is a slow, step-by-step secular process, and it's not a rapid process. On the other hand, for the bulge-dominated galaxy, or the spheroids, what you see over here is there's extremely an underdensity of galaxies in these two regions. Most of them live over here. So what you can infer is, after being formed, mostly by major mergers, they quench rapidly through the green valley into the red sequence. So we can clearly see from this picture that disks evolve secularly, slowly, step by step. On the other hand, bulge-dominated galaxies evolve slowly, faster, and they quench rapidly. So the point to take away from this slide is galaxy morphology is not interesting just in its own right, but it also gives us valuable information so that we can interpret galaxy evolution by encoding the merger history of the galaxy. So now we have established why you should care about galaxy morphology. The next thing that I want to talk to you about is why we are using machine learning to study galaxy morphology. And to do that, we need to look at what rates the various telescopes and surveys in astronomy have been producing data. So this shows the rate at which the various surveys in astronomy, which already exist or are planned for the future, the rate at which they will produce data every night. And let me point out to you that the Y scale here is logarithmic. And so what is happening, as you can clearly see, is over the last 2 decades and over the next decade, we are already seeing, and we will see, an exponential growth in the amount of data that is generated by telescopes. And it will become extremely unfeasible to process this data using traditional techniques just because of the large data volume. So by essence, using machine learning allows you to gain both time and convenience. Now, this is something that is an often advertised aspect of machine learning. But personally speaking, I also like to use machine learning due to another reason. And let's bring that up in the next slide. And to do that, I have to put 2 different approaches in perspective. First is a model-driven approach that almost all of us, so these 2 approaches have to deal with how we use data in surveys. So first is the model-driven approach. And we are all familiar with this. We were all taught how to do this from undergrad. And what we do in a model-driven approach is we start with a physical theory. We build a model for a specific data set, often with unknown parameters, based on the physical theory. We have some data. And what we do is we fit the model to the data, and from that process, extract specific parameters, and or we can also do comparison studies of different models based on the data. Now, contrast this with a data-driven approach. What we do in a data-driven approach is we specify a specific technique to explore the data. Now, based upon what we have decided how the data should be explored, the process itself generates a model for that specific data set. Now you can combine models from different data sets now to come up with a physical theory. So as you can see, these 2 processes are inherently very different. Here you start with a physical theory, and here the physical theory is just generated by the different models inferred by the data. And machine learning algorithms work primarily by the data-driven approach. And by no means I'm suggesting that the data-driven approach is superior to the model-driven approach. It may or may not be, given the certain specific situation at hand. But using machine learning at least allows us to explore problems in astronomy which have not been looked at before from a data-driven perspective. And that is one of the additional reasons that I think machine learning will also become important going forward to bring in things that you won't otherwise be able to see in your data. So, the next thing that I'm going to do is move on to the outline of the talk and start to see where we are on that screen. Oh, I think someone mistakenly annotated on the screen. Let me try to clear this up. Yeah. So let me try to stop the. Okay. Yes. Okay. So we have already finished with the motivation. So the next what I'm going to do is move into going forward. I'm going to step through 2 or 3 things. So first of all, I'm going to talk to you a little bit, give you a very brief introduction to machine learning. Thereafter, I'm going to introduce the specific algorithms that I told you about, Galaxy Morphology Network or GaMorNet. Then I'm going to tell you the results that we have achieved with GaMorNet. And finally, I will show you exactly why it is that we believe the results from GaMorNet is robust and why you should trust it. So first, let's start with some jargon and some history. Okay, wait, I'm having some trouble switching slides. Uh, okay. It seems I annotated on my screen and then I cannot select this.
Aritra, sometimes instead of arrow using the arrow, if you just click.
Thank you, RC. It worked somehow. So, okay. So, what is happening over here is on the screen, you can see different terms that are often used interchangeably when you want to describe machine learning, artificial intelligence, and all these things. But one important thing to keep in mind is the fact that these terms cannot be used interchangeably. In fact, each of these things to be a subset of the other. So artificial intelligence is an act where you would consider any machine is carrying out a task that is smart. So let's say, for example, that you have a fridge at your home and there's a dial on that fridge. And when you turn down the dial on that fridge, you expect the fridge to go to a lower temperature. That is something which is artificially intelligent, and that itself would signify artificial intelligence. Now, what is machine learning? Machine learning is only a subset of artificial intelligence. So machine learning is when machines themselves learn from the data. So coming back again to the fridge example, suppose you want your fridge refrigerator set at different temperatures at different times of the year. And you do that for a couple of years on your own. And the fridge, after a few years, has learned by itself at what temperatures you prefer your refrigerator to be by itself without any work from you. So that is machine learning, because the machine itself is learning from the data. Finally, neural networks are just a specific type of machine learning algorithms. And there are various algorithms which can help you do this. And neural networks just happen to be one specific type of machine learning algorithm. And what I want you to remember is when we talk about all of these things today, what I'm going to talk about are convolutional neural networks, which are again a subsection of neural networks. So whatever you take away from this talk, be mindful of the fact that what we are discussing today is a very small fraction of what is covered by the entire gamut of artificial intelligence or machine learning. Now, let's start with an example of convolutional neural networks, or just neural networks at work in our daily lives. Now, all of you, I'm hoping, or a large fraction of you, use Facebook. And this is one of my pictures that I had uploaded on Facebook maybe 1-2 years back. And what you can see over here is if you just dig in your browser and look at the code a little bit, then you can see that Facebook has automatically classified my image as image may contain sky, ocean, bridge, water, all of which happens to be correct. And so this just demonstrates how good machine learning algorithms have become at identifying features in images. And as you can imagine, this happens on the fly, that as soon, it takes no time, as soon as you upload an image, instantly it's classified and it's stored as what are the objects in that image. Now, exactly how is this happening? Exactly how are machine learning algorithms learning to do all this? That is to see and recognize objects in images and all that. Now, to do that, we have to do a little experiment. And all of you will participate in this experiment. And how this experiment will go is I will draw something on the screen. And this is known by many different names. Some people call this Pictionary, some people call this Scribble, there are different names. But your task is to guess what I'm drawing. You will just have 20 seconds, so be ready to unmute your microphones. And as soon as you have an answer, just say it out into the microphone, and I will stop drawing at the first correct answer that I get, okay? So as soon as I start drawing, the timer will start counting down. So
Cycle.
Bicycle.
Bicycle.
Right, that's correct. Uh, I forgot to turn on the timer. So sorry about that. But yes, this is indeed a bicycle. And I think we did it in less than 20 seconds. Uh, so what is happening over here is, okay, again, let me see. Okay, yeah, now, sorry about that. We'll have to wait for the countdown timer to stop counting. But yeah, this is indeed a bicycle. And now, and I think we did that in maybe 15 seconds or so. Now let's try to see what an actual bicycle looks like. Now, this is what an actual bicycle looks like. And as you can see, the details of my image are not at all correct. I have got the two wheels to be correct, but everything else is kind of jumbled over here, especially the lines. A real bicycle has this triangular structure. All bicycles have this triangular structure. They have this triangular frame where the pedal is running onto the wheel, onto the axle. They have this line which connects the back of the frame to the front of the frame, and some bikes may have this additional frame element over here. But instead of the fact that I completely inverted this triangle over here into something, an inverted triangle than what it actually is, I did not draw the pedals or anything. But I think by the end of my drawing, most of you were sure that I was actually drawing a bicycle. Now, it is very difficult to understand when it is happening in your brain in real time. But what is really happening is that all your visual cortexes in your brain, containing millions of neurons and billions of connections in them, whenever they receive visual input, as soon as they do that, they go and search in their repository. They have been trained from your childhood. You have been trained from your childhood to recognize images. And as soon as they do that, they go and look at these two circles, these two basic shapes, and say, oh, and some connection of lines. And they say, oh, that's a bicycle. So this tells you how you have stored visual information in your memory is you have taken visual input all your life, and you have abstracted that information by filtering out the unimportant details, such as the details of these connections. And you have stored a memory of a bicycle in a very abstract way by just remembering it's a collection of two circles with some connections between them. This is exactly how convolutional neural networks or normal neural networks work. Just like instead of biological neurons, you have what these things which are called artificial neurons in a neural network. Now, what do I exactly mean by an artificial neuron? For that, let's do and take a look at what a sigmoid neuron looks like. And this is just one specific type of neuron. And stick with me on the mathematics a little bit. I promise all of this will become clear in a second. So you can think of the sigmoid neuron as a device which can be used to take decisions by weighting evidence at different levels. So as input to the neuron, you can plug in different things. Here, I'm putting in x1, x2, s3, x3, three different values. And w1, w2, and w3 happen to be the three different weights at which I'm assigning to these inputs. B is what is referred to the inherent bias of the neuron, and A is the output. Now, how we calculate the output is we say it is the sigma of w dot x plus b. And here, sigma is just a function. So w dot x plus b is just the argument of this function. Now, how does the sigma function look like? So the sigma function kind of looks like this. So as the value for low values of wx plus b, the output of sigma, so what you have over here is the output plotted on the y-axis, and wx plus b, which is represented by z, plotted over here. So for low values of z, the output is close to 0. And this is what we say when we say rather that the neuron is not firing. Now, as the value of wx plus b grows, the output of the neuron also starts increasing. And when it crosses a certain threshold, the output suddenly goes to being very close to 1.0. And as we push wx plus b further and further, the output of the neuron finally goes to 1. This is what we call a neuron firing when its value is close to 1. And this is when we call a neuron is not firing when the output is close to 0. Now, to understand this in a colloquial sense, let's say that how can you use a neuron in your daily life? Suppose you want to decide based on the output of the neuron whether you will go to some restaurant. If the output is close to 1, you will go to the restaurant. If the output is close to 0, you will not go to the restaurant. Here are some different factors that are important in your decision. There is the ambience of the restaurant, there's the food taste and quality, and there's the quality of service. And the different weights represent how much you care about each of these topics. For example, here you care most about food taste and quality. The bias of the neuron tells you to what extent are you inherently inclined to go to a restaurant. In this example, I've set a negative value for the bias. That means I'm not inclined to go to a restaurant. And this might represent a current situation where, in spite of being a foodie, maybe you are scared because of the coronavirus to go to restaurants. And that's why you might set a negative bias for your neuron. And then you plug in different values and get output. Now, what do you plug in and values? For example, if the food taste and quality are indeed good at that restaurant, you plug in a value of 0.7. If it is bad, you plug in a lower value, say 0.2 or 0.1. And based on the output, you can take a decision. So hopefully now you have an understanding of what do we exactly mean when we talk about a collection of neurons and what does each neuron do at its core. Now let's look at what happens when we combine these neurons together, because neural networks are nothing but just a collection of neurons. So usually how neural networks are arranged is that you have these different layers of neurons. And what we want this neural network to do is kind of just recognize these 3 different digits, 0, 1, and 2. When we feed in a 0 into the neural network, we want it to say that we fed in a 0, and similarly for 1 and 2. Now, these are 2-dimensional images, but you can think about that we have just linearized the pixel values and kind of we feed that into this input layer. And in the output layer is where we expect our outputs. And the hidden layer is kind of where the neural network is doing the parsing of as I said, it's weighing the evidence at different levels and finally producing an output, which then it passes on to the next layer. So when we feed in the 0 to the neural network, we want the output of the network to be 0. When we feed in 1, we want the next neuron to fire. And finally, when we feed in 2, we want the last neuron to fire. So that is how we want our outputs to be. Now, speaking about this in a mathematical sense, let's represent all the weights in these connections. W1 weights W2 and B1, B2 are the biases in terms of vectors. We have some desired output, which we represent by YX, and we have a network output, the actual output, which we designate by A. And the input that you're giving is X. So essentially, for example, if I was to feed in 0, my desired output would be 1, 0, 0, because we want this neuron to produce a value of 1 and these two to produce value of 0s, and similarly for 1 and 2. Now, how to make sure that our weights and biases are set to such values that our desired output is always close to the network output? And this is where training a neural network comes in. Find something which is a loss function, and as an example, I've specified here quadratic cost. So you have this function which depends on the weights and biases. And what you have in this function is you are measuring how close the desired output is to the network output. And what we do is we tune these weights and biases by small amounts, and we try to reduce the value of this loss function. So this is quite similar, but not exactly similar to what is more popularly known as chi-squared minimization or many optimization techniques. And if you have tuned your weights and biases enough, then the desired outputs will always be close to the network outputs, and that's when you have an accurate neural network. So essentially, how you train neural networks is you have a collection of layers, you give it an input, see what the network is predicting. You have some inputs for you already know what you want the output to be. You calculate via the loss function how close the prediction is to the actual value. And based upon this difference, you go back and you tune the weights and biases of the network to again do the prediction. And you keep on doing this process cyclically until and unless you are satisfied that all the predictions are very close to the true target. And that is all there is to training a neural network. Now, next, what I want to talk about very briefly are convolutional neural networks. What we have been talking about are just simple neural networks, but convolutional neural networks, you can think about convolutional neural networks as just being two-dimensional upgrades to normal neural networks. So here again, you have an input layer where you feed in the image, and you have an output layer where you get your output. But the primary difference between not dense layers, which were what I was talking about in the previous layers in the neural network, and convolutional layers is that dense layers try to look for global patterns in the input feature space. What do I mean by that? That, for example, if you're feeding in the 2, it would try to recognize the 2 in its entirety. On the other hand, convolutional layers, they try to understand and find individual or specific patterns in the image. For example, in trying to recognize this 4, a convolutional layer would look at the tiny regions and try to find specific patterns. To take this example a little bit further, let's say you're trying to recognize this cat using a convolutional neural network. What the network would do is in the earlier layers, the network will look for very specific features like lines, very easy to recognize shapes such as small triangles like this. And what it will do, it will see what features are present. And based on that, based on the presence of these simple lines and triangles, it will try to decide, okay, does this mean this image has an eye? Does this mean this image has a nose? Does this mean this image has an ear? And then again, on the next layer, it will try to take the responses from these neurons. Okay, it does have an eye, it does have a nose, it does have an ear, and bingo, that's a cat. So this is how convolutional neural networks take their decisions. They learn patterns, they learn specific patterns, which are translation invariant, and then they hierarchically combine the information. That is, they take the information from the previous layers and then take a more complicated decision at the next layer, and they keep on doing this until they have reached the final answer. To talk about this a little bit more, what happens exactly in a convolutional operation is you have some input. Let's say you have this image of a 0, and the neural network is trying to find whether there is this specific pattern, this kind of inclined diagonal in this image. As you can clearly see, if you're trying to find an inclined diagonal in this image, you will find the strongest instances over here and over here. And this is kind of the output that is produced by the search. And as you can see clearly, you can see that this image represents at what locations does the neural network think this inclined diagonal is present the most. As you can clearly see, it is this location and this location. So essentially what you do in the convolutional operation is you take your filter and you kind of slide it across the image to find where exactly in that image the various features that you're looking for are present. Now, what is happening behind this sliding process is actually just a very simple matrix multiplication or a matrix convolution. You have the values for this filter and you have these values for the original input. And all that you are doing is kind of sliding your filter across the input image to produce your output, which is your response map. So I hope I have empowered you enough so that the next time someone tells you they're getting all very boisterous, that they're doing machine learning, you can tell them that all they're doing is just some botched up matrix algebra. So with that said, let me now come back to the astrophysics and talk about a very specific neural network that we have developed at Yale over the last 2 years. This is what we call the Galaxy Morphology network, or GaMorNet in short. It is a convolutional neural network. How this neural network works is we feed in the images of the galaxy in the input layer, and it predicts the shape of the galaxy in the output layer. And one of the primary features of GaMorNet is the fact that GaMorNet doesn't require too much training data, and it can be applied across different data sets. Now, why is this important? Say there's a future survey from which you want to classify morphologies of galaxies. Now, if the training process itself depends on the results of classifications from the survey, then you are stuck in a chicken and egg problem, because you cannot have the results before you train your neural network. So essentially, neural networks need to be built in such a way so that they don't require too much training data. And also, a situation where you require a single neural network for a subset of galaxies or for every specific survey is also not advisable, because then you end up with a collection of neural networks which are very specific to the task. Instead, you want things which are quite general and can be applied across the board. And that is why we think GaMorNet is pretty useful, because it has both these properties. Now, how do we exactly train GaMorNet? So what we do is, let's say we start with some galaxies which we want to test. So these are my real galaxies, and I split it into two halves. Not halves. I have a much bigger set for testing, which is about 75 to 80%, and a very small number of galaxies for training, which is about 20 to 25%. This is what we'll use at the end. But what we start with is kind of this blue circle over here. We start with a bunch of parameters. Using this bunch of parameters, we simulate some galaxies. We simulate some clean galaxies. In the next step, we pass these galaxies through a representative point spread function to figure out how this galaxy would exactly look through a telescope. Then we add noise to our convolved galaxies, which are representative of both, say, CCD noise and Poisson noise in the data set. So essentially, we have realistic simulations for which we already know the correct answer for how these galaxies look, or what the true morphology for these galaxies are, because we have ourselves selected the parameters for this simulation. So now we take the images and we infer the correct answers from these parameters, and we train a neural network. So at this stage, you have a neural network which has been trained on simulations. What you do next is you take your neural network trained on simulations, and you refine the weights and biases in that network further using a small subset of the real galaxies to finally end up with your end neural network, which you then train or which you then test on the bigger subset of real galaxies. Now, what is this process happening at the end where I'm doing this, something that we call transfer learning, which I've designated by this TL on this block over here? So what transfer learning really is that we train our entire network on simulations, and then we refine only the last few layers, that we optimize the weights and biases, only the last few layers using real data. Now, why do we do this? If you remember, I told you the earlier layers in a neural network look for very simple features like lines, shapes, triangles, all these things. It's only the later layers which combine the decisions from the previous layers into the final output classification. So we expect that the earlier layers, whatever is happening in the earlier layers, the detection of edges or shapes, very simple shapes, will be common for different surveys or even between simulations and real data. And that is why we do not need to retrain this part at all. But it's only the last part where the actual heavy lifting work is happening. Since that is very much close to the actual output, we retrain those things using the real data. And just because we are retraining only a small part of an already trained neural network, that is the reason we can get away with using a very small fraction of real data to do our training. And once you have your final neural network, we can feed in the images of a galaxy, and then at the output, we get three probability values: the probability that this galaxy is a disk, the probability that the galaxy is bulge dominated, and the probability the galaxy is indeterminate. Now, I've told you how we train GaMorNet. Now you may ask the question, okay, but to what level is GaMorNet accurate? So we have tested GaMorNet on the Sloan Digital Sky Survey and on the CANDELS survey. The Sloan Digital Sky Survey, we took 80,000 images at redshift 0. And for CANDELS, we took 20,000 images at redshift 1. For SDSS, we achieve an overall accuracy of 99%. And for CANDELS, we achieve an overall accuracy of 95%. And these things are what are known as confusion matrices. And what they tell you, I hope they're not too confusing, but what they're telling you is, for example, out of the predicted disks, 99.7% of them turn out to be actual disks. Now, if you look at this general matrix, the only region where we are doing really poorly is these bulges in the CANDELS data. And we looked at this in a little bit more detail, and what turns out to be is that the galaxies for which we get our answers wrong are essentially galaxies which are extremely small and are comparable to the PSF of CANDELS. So essentially, we did not do any quality cut on our data. But if we were to do a quality cut, say a size cut or just a cut based on how close the galaxy size is on the PSF, then these numbers would improve a lot. But we just wanted to show this result to tell how GaMorNet works across the board without any quality cuts. How does it happen when you just put all the data that you have through the neural network? As you can see, for both surveys using the same neural network, we achieve accuracies which are more than 95%. Now, finally, what do we do with these morphology classifications? And this is where the kind of color mass diagrams have made a comeback now. So what I have over here on the top panels, I have the Sloan Digital Sky Survey color mass diagrams, and on the bottom panel, I have the CANDELS color mass diagrams. And here, what you can see is that for the disk-dominated galaxies and the bulge-dominated galaxies, again, you see a lack of the bimodality. What you see here is for the disk-dominated galaxies, again, they evolve secularly. On the other hand, for the bulge-dominated galaxies, they kind of quench rapidly into the red sequence without showing any secular evolution. So, and what we gained by using a neural network is essentially we were able to increase our sample sizes for the SDSS galaxies, that we were able to improve the statistics for these kinds of diagrams by 2 times. And for the CANDLE survey, we were able to improve the statistics of these kinds of diagrams by 10 times. So that really tells you how, by using a convolutional neural network to study morphology, we have gained a better insight into galaxy evolution. So now, hopefully, you have understood to some extent what GaMorNet is, what GaMorNet does. And what I want to do for the last few slides is kind of tell you why exactly do we believe that GaMorNet works, or why exactly are we sure that GaMorNet is predicting the correct things. And we'll start with a technique which is known as visualizing intermediate activations. So this is what we do. Intermediate activations just mean intermediate outputs. So what GaMorNet does is it takes this input image of a galaxy and somehow magically passes it through all these layers and then transform these into 3 probability values. What we want to do in this technique is kind of look at the interim regions and try to see what is the output at these interim steps. And what I have plotted over here are the interim outputs of GaMorNet when you pass this single image through the network, through the trained network. As you can see, the earlier outputs are very close to the input image. Here, as you can clearly see, what is happening is here, what GaMorNet is doing, it's subtracting the galaxy from the background, because you see these 2 frames are clearly subtracted frames where the galaxy has been subtracted beautifully from the background, and it has this is the background that it's studying, and these frames, on the other hand, are studying the galaxy as a whole. There, if you go a little bit deeper into the layer, you have the network looking at sub-regions or sub-portions of these galaxies. And finally, in the last few layers is where you see very little resemblance with the input image. Now the net data has already been abstracted by the neural network to a degree, which is very close to the final output values that the network is going to produce. So that is one way, by looking at the intermediate outputs, that you get an insight into the decision-making process of GaMorNet. Now, the next technique that we are going to look at is visualizing the filter patterns. I told you a little bit before that what we do, what happens in a convolutional neural network is that the network tries to look for these specific features or specific patterns in the image. And how do we visualize the filter patterns is, what we do is we feed in a noisy image into the network, and we take the output of a specific filter. And then we optimize this image a little bit, and then we feed it again until the value from that specific filter is maximized. So in this technique is known as gradient ascent. And what we learn from this technique is exactly what these filters look like in the trained GaMorNet and what the trained GaMorNet is trying to do. So what you see over here is the different filter patterns as we go deeper into the network. And I will try to explain some of these. I won't have time to explain all of these. But what you see in the initial layers is what is happening is that the network is trying to determine very simple features like lines and edges. This is what's happening in these majority of these two filters. What's happening if you go slightly deeper is that at this stage, the network has understood, okay, the important things seem to be galaxies. And that's why it's trying to detect these circles mostly in the images. And that's what you see in these layers. If you go in a little bit deeper, now the network, after having recognized what it needs to look at, is looking at the circles in a bit more detail. For example, in the top left portion over here, the network has figured out that I need to look at the centers of galaxies a bit more closely because probably we are using it to separate out disdominated and bulk dominated, and the network decided for itself, okay, I need to look at the center a bit more closely. The final few layers, what you can see over happening is especially in this layer and this layer, in this filter and this filter, you see that the network is probably trying to look for spiral arms. Let me reiterate. We do not engineer this by hand. The network by itself learns and decides to recognize these patterns and make its decision based on these patterns. So the filter patterns give you a pretty clean insight into the decision-making process. But the last thing I want to talk about are these things which are known as class activation maps. So class activation mapping is a technique where what happens is you kind of feed in an image into the neural network, and you ask the neural network what parts of the image were important for you to take your decision. For example, there's a disdominated galaxy, so you feed it in and ask it, okay, what led you to believe this is a disdominated galaxy? So from these two images, what I have is the two disdominated galaxies which were fed into GaMorNet, which GaMorNet predicted correctly. And on the bottom panel, I have some overlays which shows the red being the regions which GaMorNet said was most important in the decision-making process. As you can see clearly, the network, because these two have spiral arms, the network has clearly picked up on these spiral arms and decided that I'm going to use this feature pretty heavily in why I believe this is dominated galaxy. And that is pretty accurate. If you are looking for spiral arms, a large fraction of galaxies will be disdominated. Let's look at the next thing. Class activation mappings can also be used in another sense where they're useful. So let's say you have this image where you have the image of the actual galaxy, but you also have some other things in the frame. GaMorNet correctly recognizes that, okay, I need to focus on the galaxy at the center and not this random galaxy at the side. And as you can see again, clearly in these images, GaMorNet correctly focuses on the galaxy at the center and produces its output. So hopefully, by using a combination of these three techniques, I've convinced you to some extent that GaMorNet and almost all convolutional neural networks are not black boxes. And the results that we get from these neural networks are interpretable, they're robust, and they can be understood. And there is robust mathematics behind this as well. It's not a voodoo which is happening with a black box. So with that said, since I don't have too much time, I will just leave you with the summary slide. And the primary takeaways is, hopefully I've convinced you machine learning algorithms are not black boxes. GaMorNet is available publicly. All the models that we trained, all the results that we have are available to the public. And finally, in the future, what we are doing is now making GaMorNet also work for active galaxies, that is AGN, besides normal inactive galaxies. And we are also extending GaMorNet so that instead of just predicting classifications, it can also go ahead and predict specific values. So that's all. And with that, I'm happy to take any questions if anyone has them.
Thank you so much, Aritra. This was a wonderful talk. So we are now open to questions. Please raise your hands or write in the chat box. Okay, so SC ma'am.
Wonderful talk, Aritra. So I have just a simple question. If you go to the to your classification, you see you have the CANDELS and the SDSS color magnitude diagram or stellar mass, the one that you got from GaMorNet. Can you go a few slides back? Yeah, this one. Now, so these things were done by people before you without, I mean, of course, the SDSS I definitely know. Now, for CANDELS also, I'm sure that people have done this without before you. I mean, you said that you have enhanced 10 times the data, right? 10 times the result data that you use to get to construct this diagram. Am I right in interpreting that?
Yes, 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 yes.
Now, my question is that other than enhancing the size of your classified objects, is there anything astronomically that you learn by having more data to plot in your stellar mass color diagram? Did I make the question clear? Do we get any other insights, or is it the same as it was when the data was 1/10 of what it is?
So the insight that we primarily gain from here is just that we achieve the same result, but with better statistics. So our interpretation does not change. So typically, I don't have this over here, but we have it in the paper. Essentially, if you just made this plot with a scatter plot instead of plotting contours, what you have very less data for is this box over here, bulge-dominated candle galaxies at redshift 1. And this is where in previous plots, maybe you have tens or hundreds of galaxies. And it's not always easy, especially if you are going to study a subset of these galaxies. For example, if you're just studying the AGN hosts. For normal galaxies, the increase in sample size just confirms the already known facts at a higher statistical level. But we are hoping, and we are almost sure that when we take this and look at subsets of galaxies, for example, the AGN, the statistics will improve to a degree that some of the known conclusions will change, or that is what we hope. They will either change or become confirmed.
So you plan to do like AGN, look at AGN, revisit AGN classification again with your CNN algorithm.
Yes, so essentially you can think about, if I'm talking about the scientific goal of the study, essentially where are the AGN in these diagrams? What fraction of AGN are in these disk-dominated plots? What are in the bulge-dominated plots? Where are they in these plots? So things like that.
Thank you very much, yeah.
Thank you, Asi ma'am. Next, we have a question from SSL.
Hi, Aritra, nice talk. I just want to clarify something. When you are showing those intermediate layers results, what are you actually plotting? Those are the output of something, or you have to convolve it back to match with your actual image?
No, this is just, for example, this first frame is just the result of, so I showed you what happens when we slide a filter across the image. So essentially, the first frame, there are many, many filters in this frame, for example, the layer 2. And the output is, I have just selected to show some of the filter output. So essentially, when you take your image, you do the filter sliding business, and what you get as an output is what is plotted over here. So this is what is the output of the filter sliding in the first convolution layer, and then in the next convolution layer, next convolution layer.
No, because I am confused because the outputs of these intermediate layers will have different number of nodes or different number of outputs of that layer.
Yes.
They're not exactly the same as with the number of inputs in the initial input layer. So
Are you talking about the size? Are you talking about the size or?
Not size. So it is a completely different of up layers. It's
sorry,
not
yes,
exactly the. Sorry.
You broke off, so I could not hear you properly. If you.
It's not exactly means to me. How can you get the similar kind of picture from intermediate layers? That is not very clear to me, or resembles something with the input, because it's a different kind of matrix altogether.
It is true that the matrix is transformed, but since this is the input layer, and if you can see, this layer is just the output of the second layer, right? So this is your input layer, nothing is happening in this layer. This is the result of the first convolution that you do. The output of the very first few convolutional layers do indeed look very similar to the input image. They do have resemblance, especially the output of the first layer. As you go deeper, then, as you say correctly, the network loses resemblance completely with the input galaxy. But especially the output of the second layer, at least we see for GaMorNet that the output clearly resembles the host galaxy or the input galaxy that we feed in, and it does not look anything like the final activation. That is, for us, we see that's a slow process which happens through the network instead just of an immediate like garbling of the data, which also might be expected.
Okay, so one more question is this kind of thing, means it was already existing in literature that you are applying for astronomical image, or something new you have added with existing structure?
Now, these techniques, all the three techniques I showed you were already known to computer scientists. So they have been around for 3-4 years now, 2-3 years now at least, and we work with some computer scientists to do this thing for our own work. So this is by no means, we did not invent a computer science technique, no.
Okay, thanks.
All right, we have 2 questions in the chat box. I think I will read it out to you. So Orgodipta says, a nice presentation, Aritra. Just one clarification I have. I have missed some portions of the talk due to poor internet connection. If I understand correctly, using GaMorNet, we are actually getting the shape of the galaxy with some probabilities. So how does it actually calculate the probabilities just seeing the image?
So as I said, the process that happens is when we are training, let me come back to my face because I don't have a slide to explain this. You can see my image, right, Nobunita, or no?
Yes, of course. Please go on.
Yeah. What happens is GaMorNet, we train GaMorNet to recognize images, right? We train it to, because when we train it, we tell it for example, when we train it with a disk-dominated galaxy, as an output, we predict with 100% certainty that that is a disk-dominated galaxy. When we do it with a bulge-dominated galaxy, we predict with 100% certainty that that's a bulge-dominated galaxy. And that is how we kind of progress. So the network learns from that, and then it kind of, when it sees an actual image, it determines with what certainty does it believe that this is a bulge-dominated galaxy or a disk-dominated galaxy. If you're asking the question how we turn that probability values into actual determinations, then what we do is essentially use a certain threshold cut. For example, for the SDSS dataset, we say that if the network is more than 80% confident that it is producing a classification of a disk-dominated galaxy, then we say that, okay, then that we classify that galaxy as disk-dominated. If it's more than 80% confident it's a bulge-dominated, we classify that as bulge-dominated. And for everything else, we put it in this intermediate bin or indeterminate bin for which we are not sure what the actual answers are. I hope that answers your question.
I think so too. Okay, meanwhile, we have another question in the chat. So Aritra says, I think I saw that GaMorNet has 3 outputs in the output layer, disk, bulge, and intermediate or the green valley. Your results mostly predicted disk and bulge, Your results mostly predicted disk and bulge-shaped galaxies, but then again, it depends on the redshift of the data which you are using to feed the network. So did you get the opportunity to get your hands on the data where the Green Valley region has more density and test GaMorNet on
that? Sorry, Nobunita, you'd have to repeat the question because it broke up in the middle.
I think my internet is unstable. Sorry, I'll repeat it. Okay, so Aritra says that in GaMorNet, there are 3 outputs, disk, bulge, and intermediate or the Green Valley. So your results mostly predicted disk and bulge-shaped galaxies, but then again, it depends on the redshift of the data. So did you get any opportunity to get your hands on the data where the Green Valley region has more density and test GaMorNet on it?
Oh, so yeah, no. So actually, what is happening is GaMorNet. For let me try to pull up some slides. So GaMorNet. I should have clarified what this intermediate value means. It just produced disk-dominated and bulge-dominated classifications. Intermediate is some things which are, it either might be in between disk-dominated or bulge-dominated, or it might be something for which the network is just not confident enough to do the prediction of it being disk-dominated. Now, this does not have, for example, if I go to my color mass diagrams, this does not have too much significance essentially when I try to say what fraction is in the Green Valley, because the intermediate classifications, we don't plot them because they're indeterminate. Indeterminate is a combination of intermediate plus galaxies for which the network is not sure enough. And this Green Valley region, inherently speaking, it has something to do with the intermediate galaxies, but not with the indeterminate fraction. And since we're not sure what the morphologies are, we kind of throw them out. So we do not include them in this study, because essentially what those galaxies are truly are, they have the bulge to total light ratio somewhere between 45% and 55%. So essentially those are galaxies for which we are not confident enough to make a call. And including them in a study is risky because they either might be bulge dominated or might be disk dominated, or even your true determinations might be off by a certain level. And that is why, while making those determinations of intermediate galaxies or that intermediate sample, we do not include that in our results. Of course, we have the data, we have those galaxies, we know how they look like, but to draw this, to be sure that when we're talking about disk-dominated galaxies, we're talking about galaxies which have not had any mergers in the past. That is the reason we kind of have to stick with only the samples that we are confident with our predictions about.
All right. We have two people who have been raising their hands for a long time now. So Choyunda, you're next.
Hi, Aritra. Can you hear me?
Yes.
Yeah, thanks for the fantastic talk. So I have a general question. So basically, you have some data, and you're trying to, let's say, predict some parameters from the data using machine learning. And so the parameters that you're trying to predict, they depend on the physics or certain physical parameters, which is already there in the input data. So what I'm wondering is, when you're using a CNN, at least the first few layers of the CNN will pick very general features, as you mentioned. But if we know what we are trying to predict, and if we know the physics or the parameters that are actually behind those, the parameters that we are trying to predict, then is it more feasible to just engineer those features from the data ourselves? Would it make the neural networks, let's say, more simplistic, because we already know what features we want the model to learn, right? So would it be better if we engineer the features ourselves rather than rely on a model and tune the model and expect the model to, at some point of time, learn the features on its own? So what do you think about that?
I think there's so one of the reasons that we use neural networks is because we don't want to engineer those features. For example, if you want to make the determination, for example, between a disk-dominated galaxy and a bulge-dominated galaxy, you might as well just take a light profile, which is very peaked, which looks like a bulge-dominated galaxy, compared to something which is very flat, which is a disk-dominated galaxy, and engineer these features into the neural network. But the entire goal of using neural networks is so that besides these features, it will also pick up on some other features by itself on the data. Now, so that is one of the reasons that you might not want to engineer features, because if you want to engineer features, then that is probably best achieved by another technique, a more deterministic technique than using a neural network. On the other hand, the second is, I think, as a practical issue. These neural networks, the bigger convolutional ones, have thousands of filters. And if you ask me to engineer features for thousands of filters, then that becomes a manual task, which kind of defeats the purpose of having to engineer the neural networks. But I get your point that the neural networks, the earlier layers are something which should be more predictable. And something that is also one of the keys that is used in transfer learning, right? Because we know, what you're saying is we know what is important for the earlier layers. What you can try to think, what is done is for example, you can even take a CNN, which has been trained to recognize cats and dogs and cars and buses, and then train it to recognize galaxies. So that transition is something where you are inherently using the fact that you know the simple features are already in that network. So I am comfortable using it in that sense. But I think if you try to engineer the features of the entire convolutional neural network, it just becomes, or even for the first 2-3 layers, it would probably be hundreds, 500, 600, or even thousands of filters. I don't think it becomes too laborious if you try to engineer all those things by hand, and kind of defeats the gains that you otherwise have with you.
Yeah, just to clarify, Aritra, that I was wondering, like, if let's say you engineer the features and you have the features that you need, then maybe you don't need a CNN. You can work with a very much simpler model, maybe not a neural network, maybe any other classifier. So is that a trade-off that we can try?
That is often done with things like autoencoders and these things, right? So you somehow identify some features that you care about, and then you kind of throw away the network with which you found out those features, and then kind of just take your inputs and then pass them through those features. So that is indeed one of the techniques that you can do, but I don't think it's exactly achievable with new convolutional neural networks, but there are other derivatives of convolutional neural networks, or such networks which can actually take some feature space, identify important features, and then you throw away the technique with which you identified those features, but then again, just keep on going with those features. Yeah, that is feasible with other techniques.
Thank you, Aritra.
Thank you, Chanda. Lopamutradi, please go ahead.
Yeah, thanks. Great talk, Aritra. So, what I wanted to ask was the confusion matrix that you showed. In general, for both SDSS and for the CANDELS data, yeah, I see that the accuracy is more for the disks compared to the bulges. So, is there any specific reason for that?
Yeah,
I mean,
sorry.
yeah,
Did you?
please. Yeah, please go ahead.
So the primary reason that we believe that the bulges are more difficult to work on is primarily to the fact that on average, bulges are smaller than disk-dominated galaxies, and more often than not, you will have some very small galaxies which are bulge-dominated, where the galaxy size is comparable to the PSA. So we primarily believe, and also you can imagine if the galaxy size is small, then inherently the signal to noise ratio that you would have for that image is low. So these are the two reasons that primarily you always end up with a slightly lower accuracy for bulges compared to what you have for.
Okay, thanks.
Thank you, Lopamutradi. SS sir, please go ahead.
Aritra, so as far as my understanding goes, it highly depends on your training set, correct? Things are dependent, not accuracy, whatever, the prediction, etc., whatever you say, accuracy, etc. So when you are training in the simulation, you have parameters which are only resemble with the physical things, or do you have things like which depends on redshift? And also, is the training set is well sampled over redshift? Because as per my knowledge goes, for higher redshift in general, if you are training with the real data, your number of samples really goes down, and that's a very major drawback of using the real data compared to the simulated data. So
yeah, those of our both those things are very valid points, and let me go back to this slide to explain this. So indeed, for the CANDELS sample, we always wanted to demonstrate by using a lower fraction of the real data. So for both sets, we used a smaller fraction. So for the CANDELS data, for example, we only had 7,000 galaxies that we used for training over here. Now, the real set of parameters that we use for our simulations are just uniform distributions of magnitude, the axis ratio, the Sircik index, and position angle. We use uniform distributions of what might be expected in galaxies in that specific redshift range. We do not try to mimic the actual distribution of parameters in that redshift range, but we just want to make sure that we are covering the entire redshift range. So that is how we select the parameters in the, for example, the sizes, the average size of galaxies that we simulate at redshift 0 is larger than the average size of galaxies that we simulate at redshift 1, just by passive evolution, because galaxies we expect it to be smaller. But since we are simulating, we do not engineer the fact that at redshift 1 we will have lower sample. We have equal number of galaxies that we simulate at redshift 0 and redshift 1, but it is indeed true that for the training, for refinement of the real galaxies at a higher level, we do get a lower accuracy, but we do not believe that we could improve our accuracies further beyond 95%. We could maybe increase it by 0.5 or 1% more, or maybe 0.5 or 0.25, even if you used a larger fraction. But as I said, in our study, the primary limitation becomes at that point that the galaxies for which we are getting wrong answers are the galaxies which are almost comparable to the ESF size of the source.
okay, thanks.
Thank you, sir. So is there any more questions? You can write it in the chat. Okay, so it seems like there is no more questions. So let's thank the speaker. So now we will move to the second phase of our meeting, that is the interaction session with the speaker. But before that, I think Ogniho has something to announce. Hello.
Okay, thank you, Nobonita. But I am sorry to inform you that the poster is not yet prepared because of lack of photo of the speaker,
all right.
next speaker. Shumolda.
It's okay. So
I'll try and I get in touch with him and then maybe prepare the poster and then share it on Facebook. So you will see it by tonight.
Sure.
Thank you.
Shumon is present in this chat. So if you are lacking
Yes.
photo, you can just ask Shumon to show his face.
Yeah,
Yes.
I think Shumanda is here.
So Shuman is here. That's right. Shuman, where is your video?